We talked about Dalton's theory, and in one of his statements he said that all atoms of a given element have the same mass. And that's sometimes called the atomic weight or the atomic mass. It's the mass of an atom, the weight of an atom. Now, we learned about the different numbers of neutrons, right? Isotopes have the same number of protons, they're the same element, but because they have different numbers of neutrons, they're not going to have the same masses. So we need to know masses of the different elements, but we're not dealing with single atoms. We're dealing with gazillions of atoms at a time, right? So what we need is the average mass. And we refer to that as the atomic mass, the mass of an atom. And this number can be found in the periodic table. Here we see chlorine's entry. Chlorine has 17 protons. The average mass of a chlorine atom is 35.45 atomic mass units. Atomic mass units are the units used to measure atomic mass, right? You see what they did there? Atomic mass units. This is the average mass. There's actually no chlorine atoms that weigh 35.45, but it's the average, right? And that's what is most useful most of the time. Unlike an average of like a regular number of things, like 10 things, where you can just take the values and add them up and divide by how many there are. We can't do that when we're dealing with gazillions of atoms, right? So we calculate the average here based on the natural abundance of each isotope. If there's two isotopes, that doesn't mean that half is one isotope and half is the other. You can't predict that. You just have to go out and measure it and see what it is. So if we look at chlorine, naturally occurring chlorine, 75.77% of it is chlorine-35 atoms. And chlorine-35, those atoms have a mass of 34.97 atomic mass units. Notice this number is very, very close to the mass number. Not exactly the same, but really, really close. The remaining percent is chlorine-37, and those have a mass of 36.97. Again, very close to 37. There's going to be some math today, so I'm going to try to, give it to you in little pieces. What do we know about percentages? They have to add up to something. 100. So if we look at the percentages of each kind of thing in a group, those percentages have to add up to 100. So if they didn't give us this percentage, we could figure it out, because with two things, it must be 100 minus the other number. So this is how we use abundances to calculate an average atomic mass. So we're going to convert the percent abundance to decimal form. So what does that mean? Well, 75.77% really means 75.77 out of 100, right? Percent literally means per 100. Well, if you did that math, you'd end up with 0.7577. This is the fraction of a whole instead of how many out of 100. So you take the percentages, you divide by 100 to get the fraction. You multiply by the mass of that particular isotope. You take the other percentage and turn it into the fraction or decimal form, multiply by that mass. You get these two numbers, you add them up, and this gives you the average mass of a chlorine atom. And you see the average is 35.45, but these are the actual ones, and nothing works there. So let's do an example with magnesium. Magnesium has 3 naturally occurring isotopes with masses of 23.99 AMU, 24.99 AMU, and 25.98 AMU. The natural abundances are 78.99%, 10%, and 11.01%, respectively. And what that means is that these percentages are in the same order as the masses, and so the first percentage goes with the first mass. And then we're supposed to calculate the mass of magnesium, the atomic mass. So I'm going to take the first percentage and turn it into its decimal form, or its fractional abundance. Take the percentage, divide by 100. And then I'm going to multiply by the mass of that isotope. And then I'm going to do the same thing for the next one. 10%, this becomes 0.1000 times 24.99 AMUs. And then the last one, 0.1101 times the last mass, 25.98 AMU. And then your calculator is going to be fine if you just type this in as it's written. So 0.7899 times 23.99 plus 0.1 times 24.99 plus 0.1101 times 25.98 equals. So that's what my calculator gives me. We should always consider significant figures, but significant figures are not super important here. Yeah?
So I remember last semester there being problems where it would give like the AMUs of the different isotopes, but not the abundance, and then it would say estimate. What's the theory behind that? Because I always get those wrong.
Okay.
I can do math, I can't estimate it though.
So there are questions like that on the worksheet today.
Lovely, okay.
Yeah. So I'll talk about a strategy in just a minute, and then I'll talk more about it during lab. So in terms of significant figures, we just want to be close to the right number. So we could look at these percentages. They have 4 significant figures. We can look at the atomic masses. Those have 4 significant figures, which is 2 decimal places. So those are kind of comparable, and so we should probably have 4 sig figs or 2 decimal places for our answer. And so it would be reasonable to say 24.31 atomic mass units. Because this is a real element, we can check it with what the periodic table says for magnesium, which is 24.3051. So if you round that to 2 decimal places, 24.31. So this is what we usually teach you in lecture. How is it calculated? And there'll probably be a question on the exam that gives you information like this. It'll be for a made-up element, though, because otherwise you could just look up the answer, and that's no fun. But the worksheet is going to have some variations of this, right? So they could tell you all but one of the masses of the isotopes, right? They could tell you this one and not tell you about that one. Well, that would be your variable then. The total, the actual atomic mass, you can look up on the periodic table. Okay? If they left out a percentage, there's one where they don't give you either percentage, and they make you figure it out. Well, then you've got 2 equations, 2 unknowns. And we'll talk more about that later. But what if you have 2 elements and they only give you one of the percentages? I think there's an example like that. Nope, there isn't. I lied. Well, again, if there's 2 things, their percentages have to add up to 100. So if there's one missing, you can find it. 3 things still has to add up to 100. If one of them is missing, you can find it. If 2 are missing, then it becomes one of those 2 equation 2 unknown problems. Any other questions about those? Yeah, we'll talk, yeah. I don't feel there's any point in going over it right now because you don't know what the problem is. And I'm going to throw a lot of other stuff at you, and it'll just fall out on the floor anyway. So we'll just put it in later. How do they measure percent abundances?
Moles.
No, not actually moles. But I'm talking about the physical technique, right? You know, you can't just like sort through a bunch of nails and, okay, there's this many of this kind and that many of that kind, because these things are too small to see, right? They use what's called a mass spectrometer. And I'm not going to quiz you on how this works, but I think it's useful to at least hear about it. So you put your sample in here. So in the previous example with the chlorine gas or the magnesium, you would put your sample of the element in here, and then there's a heater here that vaporizes the sample. You can even take metal samples and get them to be vaporized in the gas state. Then it comes through here where there's an electron beam that ionizes the particles. So we're shooting electrons at it, and some of those are going to stick and make charged particles out of these guys. We want charged particles because then we can use an electric field to accelerate the particles. We want them moving faster and in the same direction. So we've got these charged particles now, and they get accelerated here, like one of those little Hot Wheel things with the rollers. It goes whoosh, and then it comes through here, and here's a magnetic field. Because they have a charge and are moving, they will interact with the magnetic field. The lighter elements, the lighter isotopes, will get bent more by the magnetic field, and the heavier ones will be bent less. So if you think of a wagon rolling down a hill, and you're standing here and you're trying to push it out of the way because, I don't know, maybe there's a child there or something. If the wagon's empty and you give it a shove, it's probably going to move quite a bit, right? And you can get it to go off at an angle. If it's loaded with bricks and is really heavy, you can give it that same shove and it's just maybe going to move a tiny, tiny bit, right? That's how it works with these isotopes. So the lightest particles move over the farthest, and the heaviest particles don't move very much. So we have a detector here, and we can get an electrical signal, and we can see how many ions are hitting in each place. Any questions? So the sort of information you get is something like this, where it's giving you the mass number, and then it's giving you the intensity of the signal for each of those. So the highest one is always given 100%, and the rest of them are whatever fraction of that they are. So the position of the peak indicates its mass. The intensity, or the height of this peak, tells us the relative abundance. I am not going to make you do these calculations, so I'm not going to talk about it.